No, that's okay. I think it's good.
No, it's not working again. There's room next door though, okay? I did report it, but haven't fixed it yet. Okay. All right, so as I said last week, basically what we're going to do this week is basically finish off all the different types of integration strategies. So last week we basically just reviewed integration and the technique I'm assuming everyone's already familiar with, which is what I call integration by basic substitution. Now, because basic doesn't mean easy. Basic means the substitution should kind of be staring you in the face from the question. We also did how to handle products of sines and causes, and depending on the power and things like that. As I explained, with trig integrals, what you should do when you get the hang of it, it's not too bad when you get the hang of it. When you look at the formula sheet, right, as I explained, this actually has, for integration in particular, this actually has a lot more information than you realise. Right, so the right-hand column is the integral. Sorry, I have a splitting headache and it makes my sound like a drunk. So the right-hand side is the integral of the central column, but the central column is also the integral of the left-hand column. So there's actually a lot of trig integration in there without realising. Right. So for example, if you look at the left-hand column, if you've got say the integral of sec squared or cosec squared or tan, you look here first. If it's not there, you try a simple substitution first. If that doesn't work, then you do what we did last week, right? If there's, turn everything into sines and causes. So remember, tan, cosec, sec and cot can all be written in terms of sine and cos, and try what we did last week. Also remember, of course, integration can't always be done. Unless I royally stuff up though, I won't give you one that's impossible. It's got to be done somehow. The other problem with integration is I can't, unlike differentiation, you've got the product rule, the quotient rule, the chain rule, and that's it, right? And it's usually obvious what you've got to do. If it's a product, you use a product rule, ratio, use the quotient rule, function within a function, use the chain rule. The problem with integration is it takes a bit of skill to work out what's the best way to attack it. The only sort of hint I can give you is that if there is a square root in the integral, you will do whatever it takes to get rid of it. Right? So a couple of the examples we did last week, something like if you have to integrate x times the square root of x squared plus 1, You would let u equal what's under the square root, because you want to get rid of it's probably the wrong word. What you want to do is turn it into u to the half and hope everything else works itself out. Right? That's the aim. Square roots are always problematic in integrals. So much so that there is a method, probably one of the most powerful methods of integration we have, because you can actually make this work for any square root, right? No matter what, we're only going to use it for these three cases, but you can actually force this one to work for any integral that's got a square root that you can't get rid of by a simple substitution. Right, so this is a very powerful method, although we're only going to use it for this three. This is called integration by inverse trig substitution. And this method is solely designed to get rid of a square root. Right, that's its sole purpose. Right, this table is on the formula sheet and it tells you what to do. Right? So if you've got an integral that's somewhere in there, it's one of these three square roots, and you can't get rid of it by a simple substitution, like i.e. letting in the first one, if the substitution u equals a squared minus x squared doesn't work, try this. If it's a squared plus x squared and u equals a squared plus x squared doesn't work, you try this. Right? So if you've got one of these square roots that you can't get rid of by a regular substitution, this is your change of variable. Right? Now, this is called inverse trig substitution. Now, recall from last week, what we were doing is we let u equal something involving x. Right? Notice these ones are backwards. These are x in terms of u. But technically, if I solve the first one, if I rearrange the x equals a sine u is the same as u equals inverse sine of x on a. Hence, inverse trig substitution. That's what you're doing. Right? It's just hidden. You know? You use that substitution. Now, this third column is not important for us, right? I'll show you why this is here, but you're never going to need this column. But I'll show you why there is a restriction on u in a sec. And then you use this trig identity, which will magically get rid of the square root, right? And you can see what's happening. If you've got the first one, a squared minus, a is a constant that's given in the question, right? So you can always figure out what a is. If I substitute x equals a sine u into that square root, I get a squared minus a squared sine squared. Yeah? Take out the common factor of a squared, it becomes a squared all multiplied by 1 minus sine squared. Replace 1 minus sine squared with cos squared from the fundamental trig identity. This becomes the square root of a squared cos squared, which becomes a times cos. Right? And we only ever take the positive square root. That's what this column's telling you to do, right? The restriction on u means usually when we take a square root we do plus minus, yeah? We don't with this one. You always take the positive, right? And that's because of this restriction. So this isn't really important. All that this column means is take the positive square root. That's all it means, okay? And then, so your square root disappears and becomes a times cos. Now, of course, though, what else is going on in the problem? You might have sines and coses in there. What the aim is, this will become a trig integral like last week, right? And then you can do it, okay? So this table's on the formula sheet, so you don't have to memorise it, right? And as I say, it tells you what to do. It's called an inverse trig substitution because what we're actually doing is we're letting u equal inverse sine of x on a. And what will happen is that square root will magically disappear. It's not magic, of course, it's maths, right? But it will get rid of the square root for you. We take the positive square root due to the restriction placed on u in the third column, right? Then what you hopefully end up with is an integral involving sines and coses, or what the trig functions that you can handle. That's the aim. Once you do it, though, how do you go back to x easily? Well, the way we do that is we use a little reference, what we call a little reference triangle. Now, when we first all learn trigonometry, right, the sine, cos and tan, we do it with right-angled triangles, don't we? And in WA, you learn it by that, it's Sokotoa, isn't it? Yeah? So I did this I learned trigonometry in New South Wales. We didn't use a word, we used a limerick. And unfortunately, being an immature 17, 16-year-old boy, I changed the words. That's now the only one I remember, and mine is not to fit, say, in public. Right? So I remembered it as some old something can't always hide their open something. Right? You could probably use your imagination to figure it out. Right? But however you remember it. But the key is, like all the algebra laws, this works no matter what. Now, what we normally do when you first learn, you're given a right-angled triangle, you apply SOHCAHTOA. But it works the other way. Given SOHCAHTOA, there exists a right-angled triangle with those properties. Right? It has to. Right? So if I've let x... So basically the substitution here is x equals a sine u. That's saying sine u equals x on a, isn't it? Right? That means that there exists a right-angled triangle with angle u, opposite x, hypotenuse a. It has to exist. Yes? Right? You can find the length of the unknown side by Pythagoras. Right? So of course we know that this squared plus this squared is this squared. If we know these two, we got the... And notice this will always be the exact square root you were trying to get rid of in the first place. Yeah? Then from here you can figure out all of the trig functions in terms of x and a as you need them. Yeah? And so I think in the formula sheet I've got these, if we have a look at them, I think I've even got the little, yeah. Right, so I give you the table and I'm even kind enough to give you these three little right angle triangles, right? The little reference triangles to return back to x. Because remember, as a substitution, you're bringing in a u as a tool. When you're done, you've got to get rid of it, right? And then, of course, to do the change of variable, normally what we do is we find du on dx, right? And then write du equals something times dx. Right? Here you can skip that. You just find dx du and then solve it for dx. So you just get a cos u du. So that's all you change a variable. Right? And the hope is it becomes something, a trig integral you can do. Right. And then the other two work a similar way. So if we've got a squared plus x squared, we instead use the substitute x equals a tan u, which is technically u equals inverse tan of x on a. Right? So inverse trig substitution. Then the a squared plus x squared becomes a squared plus a squared tan squared. Factor out the a squared. 1 plus tan squared is sec squared from the fundamental trig identity. And then you take the positive square. The square root disappears. Right? And you're left with a times sec. And then hopefully all the other change of variables will sort itself out, giving you an integral you can do. Then reference triangle here, we let tan of u equals x on a. So tan is opposite over adjacent. Right? So there exists a right angle triangle with angle u, opposite x, adjacent a, unknown side by Pythagoras. Oh look, the exact square root you were dealing with in the first place. Right? And that'll let you go back to x. And then of course we need x is a tan u, so dx du is a derivative of tan of sec squared. That's how you do your change of variable. The last one is a sec u, which is technically u is inverse cos of a on x, because remember sec is 1 on cos. Right? Remember the other three trig functions, cosec, sec and cot, do have inverses, but they're frickin' awful to use. We don't use them. Right? We just turn back to sine, cos and tan. Right? Now when you've got an x squared minus a squared, you'll get a squared times sec squared minus 1. Sec squared minus 1 is tan squared. Gets rid of the square root. You take the positive square root because of the restriction placed on u. Right? And then a little reference triangle. Here we've basically got cos of u equals a on x. So there exists a right angle triangle. Cos is adjacent on hypotenuse, where this is a, this is x. The unknown side by Pythagoras. Again, precisely the square root you were trying to get rid of in the first place. And we also need the derivative of sec, which remember is I give you. Like, even I don't remember the damn thing. Right? Derivative of sec is tan times sec. Oh, where'd it go? Right? And off you go. Right? So this one's very powerful. You can actually use this one whenever there's a problematic square root. You can use this one. This is probably one of the most powerful integration techniques we have. Right? Because you can force it to work. I mean, if you've got, not that I would give you one like this, but you know, if you had something like, you can always make this work. So let's say you had an integral that involved that, say, right? and a simple letting u equal 1 minus x cubed is not working, and integration by nothing else is working, you can actually make this one work by doing that change of variable. Right? And you can force it to work. Right? But when you do your change of variable, it will become messy because you'll have to differentiate this implicitly. But the key is that this method actually is really, really powerful. But we're only going to do it with the three I've given you. Basically come on. Right? One of these three. Okay? So again, the way we do these ones, if you've got a square root in there and a simple substitution isn't working, you do this. Right? And hopefully this will work. Right? Now there's an example in the lecture notes in here which I'm going to do by hand. Right? I'm actually going to do this one. You don't have to write it, it's already in the lecture notes. I just want to show you. Because this one sort of illustrates a lot of pitfalls with this method. Let's say we've got to integrate, where am I? Right in front of me. So we've got this one. Now, what you might try first is you'd let u equal 9 minus x squared. That ain't going to work. If it was x over the square root of 9 minus x squared, life is good. Or if it was x cubed over the square root of 9 minus x squared, you could make that substitution work if you had to, right? But the x squared's not going to work because if you do, I'll show you what happens. If you do this, this will become now let's take that half out. One of the x's cancel. Oh crap. Right? Now what you could do is, well, you don't want to do that, right? Because then you'll have two integrals to figure out, and that's still not pleasant. Yes? Yes. Right, it's not going to work anyway, so who cares? Right? But yes, right? Never, ever, ever use this to introduce a square root. You want to get rid of them, not bring them back in. Right? So that's not going to work. You could do it. It could, but it's actually not very pleasant. And you'll have two integrals to figure out. Right? What'll happen is it'll split into cases. We don't want to do that rubbish. Right? So in other words, a simple substitution's not working. Right? So in that case, we try an inverse trig substitution. So we look at our table, we see we've got a square root of a squared minus x squared is what's causing the problem. So in this case, a is 3, you know, right, because it's 9. Right? So the table tells you what to do. I'm going to let x equal 3 sine u. So technically, u is inverse sine of x on 3, hence the term inverse trig substitution. As always, so I get dx. All right, that's what I'm going to replace dx with. And what will happen to the square root, when you get the hang of it, you can leave this step out. So this is 3 sine u all squared. That's the point. That is the whole point of the method, is to get rid of the damn square root. If the square root hasn't disappeared, you're not doing it right, because that is its sole purpose, right? So the square root will disappear. So the integral becomes x squared is 9. The square roots disappear to give, and then the change of variable. All right, and now you have fingers crossed and hope this is doable, right? Which, unless I stuff up, will be. So let's clean this up. We've got to... as always, I take the constants outside so they don't annoy me. Oh, that I can do. That's from last week, right? Even powers half angle formula, right? So I replace sine squared with a half times 1 minus cos of 2 2u, right? And I always take the constants out. You don't have to. It's just something I do, right? So sine squared is a half times 1. Sine squared of u is a half times 1 minus cos of 2u, right? That I can now do. Just don't forget to bring the constant along. Integral of 1 is u. The integral of cos is a half. Remember, of course, if you need to do the simple substitution separately, do it. Okay? Yeah, obviously don't use u, right? Use v or whatever the hell, right? Then we get Now we need to go back to x, right? Now what you could do, which some textbooks do this, it's terrible, but u is basically inverse sine of x on 3. Right, but that's not the right way to do it. Right? Now, obviously, the first term we can't do anything with. The second one will simplify. Right? You can actually get, because sine and inverse sine are inverses of each other, and because sine and cos are linked. We don't do it this way. Right? So this first bit's fine. Right? That's fine. And the second bit's not. That's not an acceptable answer. What we do instead is we turn it into something involving sines and coses. Right, so we can use our little reference triangle. So instead of from here, what you do next is you say this equals, so sine of 2u is 2 times sine of u times cos of u. Right? Then it's much simpler and you'll get a much nicer looking answer. Draw your little reference triangle. Basically, we're letting sine of u equal x on 3. So that means there exists a little right angle triangle with angle u, opposite x, hypotenuse 3. This thing has to exist. Yeah? Length of the unknown side pi Pythagoras. That's the square root I was getting rid of in the first place. That's got to happen. Right? Now from this, I can now figure out what sine of u and cos of u are. So then I can say, so this is 9 on 2, sine of u is x on 3, cos of u is the square root of, right, and then just cleaned it up. So, yes? Sorry? Oh, thank you. Right, done. Right? So we use the little reference triangle to make it easier to go back to x. Now, of course, you can always check your answer by differentiating that. Right? This is the thing. Often differentiating it and checking your answer is more work than doing it in the first place. But you could, right? And of course, differentiating that is a lot easier than differentiating this, right? But so we don't write our answers like this, right? But you could check. Don't do it as quickly as me. Now, derivative of this.
You dropped the minus sign.
Yes, I did. Thank you. Well, that would have stuffed everything up. Now, derivative of this is, again, please don't do it as quickly as. Ugh, freaking product rule. Second bit times the derivative of the first bit plus the first bit times the derivative. Again, you don't have to do it as quickly as me, right? Now, yeah, that's a sixth. Now take out the fact that they're that. What will happen? That's a sixth times 3. That's a half. That's a half. That's a half. That's a half. So that one cancels with that one. Hang on. No, it doesn't. X squared. Hang on. What have I done? What? No, hang on. Let's do this properly. So if I take out the 3, this will put a 3 up the top. So there's 3 up the top. 3. That's 9. And if you give all that a common denominator, believe it or not, you will get there. Right? A lot more work though, wasn't it? Right? But you can always check. And the key is that doing it, writing your answer, this would be a lot hard to differentiate. And because the trig functions are linked and the trig of an inverse trigger, it should simplify somehow. You can do it that way, but it's much easier just to use the little reference triangles. Okay? But the main thing is when you use a triangle, reference triangle, you've got the angle U, you don't know what 2U is. Right? Don't just double everything in the triangle. Trig doesn't work that way. Right? So just to turn everything into just sines and coses of U, then you can use a little reference triangle and make life easy. Okay? Now, there's a couple more in here. Let's have a look at some of these ones. All right, let's have a look. Let's have a look at this first one. Now, this first one can be done by a simple substitution as well, right? Because if you let u equal 1 minus x squared, actually, I'm going to do it. I'll do it the other way and show you get the same answer. But let's, for the moment, just use an inverse trig one, right? So I can see a simple substitution will work, but it's not immediately obvious it will work. Right? So let's just do an inverse trig. Here we've got an a squared minus x squared where a is 1. So we let x equal sine of u, dx is therefore cos of u du. The square root will just become, instead of being 1 minus sine squared, it'll become cos squared, you get cos. And remember, the restriction in the table means you only ever take the positive square root. So the x cubed up the top, we've got a sine cubed on cos times cos, clean that up, and the hope is it becomes something we can handle from last week. This one is. We've got an odd power. You know the trick, peel off one of the odd powers, write that as sine squared times sine. Make everything to the left and to the right the opposite trig, replace sine squared with 1 minus cos squared. Have to do another change of variable in this one. Right? Obviously don't use u again, otherwise that's going to confuse the hell out of you. Right? Pick the next letter, v. Or pick whatever you want. Apple, whatever the hell. I don't care. Right? If you can draw an apple well, go for it. Right? This becomes v, then work your way back. V is cos of u, and then to replace the cos, little reference triangle. We've let basically x equals sine of u, so that's sine of u equals x on 1. Right, so there is a little triangle where this is u, opposites x, hypotenuse is 1, unknown side by Pythagoras, precisely the square root you were trying to get rid of. Right, and then you can say cos therefore is x, is the square root of 1 minus x squared on 1. Right, done. Now you could do this by a simple substitution as well. Right, just to convince you get the same answer. Let's do it. Now if I let u equal 1 minus x squared, du on dx is minus 2x, so dx is minus du on 2x. So this becomes clean this up. So what have we got? Let's take out that half, as I always do. Then I could use this if I wanted. This says x squared is 1 minus u. Now I'm getting somewhere. So 1 on u, that's u to the minus a half. U on u to the half is u to the half. Awesome, right? So you could do it that way, right? But this, oh, I'm sorry, obviously can't look behind me, but you can see, like this one, you've had to use this, so this by simple, although it looks like it's saved you more work, the trick is you have to have spotted this, you know? Right, whereas the method inverse trig one, it just works, yeah? So although it seems more work, really powerful method, because it often will work for integrals where a simple substitution won't work. Right? But you can see there, that answer is entirely equivalent. Obviously, the terms are written the wrong way around. Right? But it's the same. Yeah? Right, got a couple more there. 1 over the square root of 16 minus x squared. Now, this one, if you look at the formula sheet, this one is dangerously close to looking like that one, isn't it? Ooh. Right? Only a couple of constants in there. Yeah, we don't worry about it. Constants come along for the ride. So I suspect that this one will involve inverse sine of something. Yes? Right? There'd be some constants in there, but you know, it's almost there. Right? Not quite though. Right? So no, certainly no substitution is going to help. Simple substitution is going to help here. If you let u equal 16 minus x squared, you're going to have an x floating around, and you do not ever use that to bring in another square root. That ain't going to help. Right? So, inverse trig. This is an a squared minus x squared, where a is 4. The table tells you let x equal 4 sine of u. Go through the process. Ooh, right? As I suspected. Yeah? Right, so the formula sheet sort of gave you a hint, didn't it? Right? There's, you know, it's one. This formula sheet's 1 minus x. This is 16. But surely that, you know, yes, there'll be a 4 somewhere, but you know. What about this one? Now this one, a simple substitution will work. This one is actually easier to do by a simple substitution, because if I let u equal x squared minus 1, the derivative's 2x. That's going to get rid of the x up the top. Done. Right? But I'm doing this to show you, it doesn't matter how you do it, right? If you do this one by inverse trig, it should still work, and of course it does, right? This is a x squared minus a squared, where a is 1, right? So a little table tells you we've got x squared minus a. So we've got this one, yeah? So we let x equals a sec of u, right? We do the process, they use that trig thing to get rid of the square root, right? And you get to here and think, oh, crap, right? So remember, the methods we went last week only worked for products of sines and coses, not reciprocals. That's technically 1 on cos squared. So when this happens, you go, please let the formula sheet help me. Right? Yes. Right? Done. No? Right? Little reference triangle. And that one's actually easier by substitution. We're just showing you will get the same answer. If I did a simple substitution, again, and for whatever you do, don't do this in your head like I'm about to. Do as I say, not as I do. Let u equal x squared minus 1. This will become a half times the integral of u to the minus a half, which is u to the half plus c, which is x squared minus 1, the square root of x squared minus 1 plus, done. Right? Don't do it like that though. Right? Right, it's a really powerful method because you can make it work on all sorts of ones. Basically, whenever because I'm an applied mathematician, I do a lot of calculus, which means lots of integrals. And whenever I get a problem with a square root, I almost always revert to this method because I can always make this method work. Right? Very powerful method, this one. Really good because it gets rid of problematic square roots. Right? But for our purposes, we're just going to use it for these ones. Right? And again, this is on the formula and it tells you what to do. Right? Okay, how much time have we got? Oh. All right, now there's another method. The next method is a weird one. Now, the only reason I really show you this one, and this one is not in every textbook, right? This is a weird method. The only reason I actually want to show you this one is because I don't like giving you this thing without at least telling you where these formulas come from. Now, as I explained, all of the integral formulas, so the integral formula for log of x and the 3 inverse trig functions that are on the right here, we're going to prove those using integration by parts. That's the last method we're going to do. The integrals of tan and cot are simple substitutions because tan is sine on cos. You let u equal cos, it becomes the integral of 1 on u, which is log of u. That's where it becomes log of sec, or and cot becomes log of sine. The 2 for cosec and sec, however, right, they need a special technique, right, which is what we're going to do next. Right, but this is a weird one. Basically, I only show it to you to show where these 2 ones come from, and after that, we'll probably forget about it. Right? This is a strange one, but there's a couple of reasons I like this one. We've done how to handle products, and of course that's the one I did by hand, right? We've learned a technique on how to do products of sines and coses, right? What happens if you have a rational function involving sines and coses, like the integral of sec? So that's the integral of 1 on cos, right? And of course no simple substitution is going to work, right? There is this method that will let us handle rational ones. The reason most people don't use it, or it's not taught that often, is twofold. 1, it's weird. And 2, when you do go on in maths, if those of you who are studying maths anyway will go on and you'll do integration of functions in the complex space. So the integrals of complex functions. So functions involving the complex numbers. Everyone knows what a complex number is, don't you? A plus I times B, yeah? And very, very awesome stuff, actually. Doing calculus on complex is actually easier, right? It doesn't seem like it would be, but it is. And when you learn the technique, it's called using the calculus of residuals. And the catch is that when you do integrals in the complex plane, you're not integrating across the real x from a to b, you are integrating over regions in the complex plane with the real and imaginary axis. So it seems like, oh my god, right? But it actually is very straightforward and extremely powerful. Like, you can do all sorts of real valued integrals using complex functions, and it makes life easier. And it's all because of Euler's famous formula that, you know, a complex number can be written as r e to the I theta. Everyone remember that? Or cos theta plus I times sine theta. That means the exponential trig functions can be written in terms of exponentials, and integrating exponentials is awesome because they're so easy. Right? So you'll learn that later, if you do that, you'll learn later on, if you've got ratios of rational functions involving the trig functions, you do it with complex it's actually easier. However, I can't expect you to do that. You know, getting to that level requires doing complex function theory first, which we don't do in first year. So anyway. But the other reason I like this method is, remember that comic I showed? Integration is hard. Right? It really is. It's not like, although it's the opposite of differentiation, it's not pleasant. Right? It can be really tricky. And sometimes you need methods that initially you'd think, how the hell is this going to work? But it does. Right? And that's what makes integration so fascinating, to me anyway. Right? Maybe not to you, but to me it does. Right? Last week we looked at trig intervals involving products of sine and cos, but if they involve quotients, we need a different method. This is the substitution we use. What? So if I've got let's think of I want to prove, hang on, which one do I prove? I want to prove that the integral of sec is log of sec plus tan. All right. That is the substitution I'm going to use. Right, it's called so I call them a half angle substitute. Some people call them a double angle substitution. No frickin' difference, right? Yeah, it's either half of something or double of something else. You know, that's what it's usually called. But look at it. Let u equal tan of a half x. How is this supposed to work? How is this going to help me? This will always turn an integral involving a quotient involving sines and cos into a rational function of u. Now, the next thing we're going to do is a technique to handle integrals of rational functions, right? So we'll cover that in the next section, right? Now, the reference triangle for this one, this says tan of x on 2 is u on 1, yeah? So there exists a little triangle that's got angle x on 2, opposite u, hypotenuse 1, adjacent 1, so the hypotenuse is the square root of 1 plus u squared. I can now use this to figure out what is sine of x and cos of x in terms of u. So sine of x, which is 2 times sine of a half x times cos of a half, remember half angle works, we know it as sine 2 theta is 2 sine theta cos theta. It works no matter what theta is. Replace theta with x, it works. Right? So 2 times sine of x times cos of, I can figure out sine and cos of x on 2 from my little reference. That becomes 2u on 1 plus u squared. Cos of x, half angle formula is cos squared x on 2 minus sine squared x, or 1 minus 2 cos squared x on 2, or 2 sine, whichever order it is. Even I got to look the frickin' things up. I mix them up all the time. They're all on the formula sheet, remember? I can write cos of x in terms of u, and I need my change of variable. If I've let x equal 2 inverse tan of u, dx on u is 2 times the derivative of inverse tan, off the formula 1. But again, you look at, there's no frickin' way this is going to work. It does. It does. Right? This is a weird one. Like, the thing I like about this one is this method, it doesn't appear to work. This isn't going to help, but it does. You know, and that's the thing with integration. Sometimes you need really weird substitutions to get anywhere. Right? And this is a skill that comes with years of practice, right? Not just a semester's worth, years and years, right? Right? And this one actually proves it. I'm going to do that in the next lecture. What I'd like you to do, more importantly, please practice the inverse trig substitutions and read these 2 slides, please, and make sure you understand where all of this comes from first. Then we'll do a couple of examples with this one, okay? But we'll leave it there for today because we're almost out of time. All right, and I'll see everyone tomorrow.